We're continuing our discussion on multiple variable regression. In our previous two videos, we looked at logistic regression, predicting the probability that an event occurs. So they buy from you, or in our examples, we could identify that the penguin was a Gen 2 penguin. So it happens or it's not, right? So it's a yes or no with the logistic regression. We looked at Poisson regression, which looks at number of counts. So we looked at, in that case, the number of stop and frisk stops. That you could look at Poisson regression for the number of absences. We could build regression models for the number of birds. So it's any kind of count. It's a whole number. Linear regression is what we're going to look at in this video. And in linear regression, we have some kind of measurement. So we're assuming that the data that we're trying to predict is continuous, so it can be fractions of numbers. It's some kind of interval ratio data. Now, when we look at multiple variable regression, we have multiple variables that are predictor variables that we're using to predict some other variable. So we have multiple independent variables used to look at the impact it has on the dependent variable. Okay, it's important to note there is a difference between multiple variable regression and, as I scroll down, and multivariate regression. So multivariate regression is where you have more than one outcome variable, more than one dependent variable. So for example, we would create a model to predict scores, but they could be math scores or English scores. And then we have a set of independent variables like attendance, IQ. You can't see my face is covering the one that says income. So we can have multivariate regression where we have multiple outcome variables. We're not looking at that here. When you look at multivariate regression, we're now dealing with matrices and linear algebra. And so for the most part, we would do is we would just create in real life more just separate equations, separate regression models for math scores versus English scores, rather than kind of trying to combine it all together to look at it combined. A multivariate regression model has the same predictor variables. So we would predict math scores with attendance for both, and then we'd predict English scores with attendance. But the amount of impact that attendance has on math or English could be different. So that coefficient would be a different number when we look at the impact. So that's how multivariate works, but you could also just create two separate regression models, one that figures out which variables impact math scores and one that looks at which variables impact English scores, rather than trying to do it all together and dealing with matrices. So what we're doing here is we're doing multiple variable regression and linear regression, where we have one predictor variable that is a measurement, and then we have one predicted, one dependent variable that is measurement, and then we have multiple predictor or independent variables. So let's take a look at an example. If you're working along with us, we are at Dr. Steph Powers. You can't see that, it's up here, drstephpowers.github.io/BIA/ and we are here in chapter 10 under regression. Working through this workbook. To open this workbook, click on Open in Collab. When you do that, you will need to log into your Google Drive. You will need to save a copy to your Google Drive so that you can run the code and amend the code. In this particular data set, we are going to be using this data set here that is called fundamentals. You can find that data set if I go back to GitHub under data and you scroll here, you can see here's the fundamentals. So you can download this file, your little download button right here, and then dump it into your Google Drive. Because the first thing we're going to do is link this data set to our workbook. So you need to dump the CSV file into your Google Drive. All right, so now let's go find it. So we need to import pandas as PD. So if you did not do that from the previous videos, then start at the very top of this workbook with that first line of code. Once you have imported pandas from PD, then we are going to link our workbook to our Google Drive. So really it's just asking you whether Google can have access to your own Google Drive to link your workbook with your data sets. Make sure you hit continue and select all to get it to give you access. All you're doing is giving your workbook access to your drive. You're not giving anybody else access to it. Okay, so once we've linked that, we can import our CSV file, doing read CSV and saying where it's located. So mine is located in a folder in my Google Drive called BIBA Handbook, inside another folder called Chapter 10, and that's where you'll find this fundamentals.csv. So change out this portion of the code to locate it to where it is inside of your Google Drive. If it's just straight into the drive, then just remove those two sections entirely so it goes directly to that file. So we import it in. This data set is a New York Stock Exchange data set originally from Kaggle. So if you want to go get their data set, you can do that as well. And so we can look at the first couple rows to see what's here. What we have is we have a number of different stock tickers, and it has their income statement, balance sheet information here. I think I've simplified their full data set to be smaller. So that's what you're seeing, I think, if you look here rather than the full one. And so right now you can see we have information for different years for Apple stock or whatever this AAL is, some other company. But you can go through and there's a bunch of different companies, but it has multiple years for each. All right, so we are going to use this data set even though we're not going to use it appropriately. Because in this case, the method that we're using for our linear regression, we are going to assume that every row here is a different company, rather than recognizing that the first 5 rows are all the same company and it's a different period of time. So we're going to start off and just use the data, but we're going to use it incorrectly. So please note that if this is what you're doing for a living, don't do this with this data set. We're assuming here that these are all independent of each other, that these are all separate tickers. Okay, so if we were to do that, then we could take the other variables and in this case, let's suppose we want to predict earnings per share. Okay, so we're going to take this data and we're going to say, can we take some of these other financial ratios and use them to predict the earnings per share? So for example, let's suppose that we take cash ratio, after-tax return on equity, gross margin, and current ratio. Could we build a model that predicts earnings per share? So earnings per share is a number that can have fractions, so we can use our linear regression model. When we are doing this linear regression model, we are assuming no multicollinearity. That is, these variables are independent of each other. If you've taken some accounting, some finance, if you know how financial statements work, you know these are not independent of each other. We have a multicollinearity issue. So we'll actually look at this data as we test the assumptions in a moment. We'll look at that multicollinearity issue. So we know already that we are 1, using the data set incorrectly, and 2, this is not a good model because we have multicollinearity, because those variables we're using to predict earnings per share are highly correlated with each other. Okay, so knowing that ahead of time, we know to look for that in our own data sets as we do this. So if we're going to create this model, we could do this with sklearn using the machine learning methods, linear regression here. And as we talked about in the Poisson and in the logistic regression model, you can use these machine learning methods for regression, multivariate regression, but note that these are designed for focusing on the prediction, focusing on what the earnings per share are, as opposed to the statistical significance of the variables you're choosing. That is, it'll give us the prediction of earnings per share based on cash ratio, after-tax return on equity, and all these things, but we don't actually know if those variables are important beyond just this sample data set that we're playing with. Okay, what we really want is, because we want to actually know which variables help us determine earnings per share, which ones are related, are correlated between the independent and the dependent, not between the independent and the independent, that we can then use them to determine future earnings per share, because we can say based on this cash ratio, the earnings per share will be how much. So here we also want to look at statistical significance and what those coefficients are. If we're just using sklearn and we're using machine learning methods, it doesn't focus on that. So let's do that piece first so we can see what it looks like, and then we'll use a statistical package to see the difference. All right, from sklearn, we're using a linear model. These are all generalized linear models. This one is linear regression. We have this data set here. We're going to pull and separate it into our test and training data set. That's this line of code that we see here. We are ultimately going to take the data set and we are going to make 20% be our test, and the rest of the 80% we'll use to build the model. So we build the model and get our algorithm, and then we can use the test data to see how accurate it is. Okay, so we are going to need train test split. In terms of measuring the accuracy of a linear regression model, we can't use accuracy like we did with logistic, because that was just a label yes or no. Here we need to look at the size of the measurement error, the difference between the predicted value and the actual value. So measurement error, you'll recall, is actual minus predicted. If we are looking at it within the training data, it's called residual. If we're looking at it in the testing data, it's called measurement error. Okay, but same thing, distant difference between the actual and the predicted. So we can use that to figure out how well our model fits. So we're going to use mean squared error. That was one of the methods we talked about. We talked about measurement error. And then the other thing we can look at is R squared. How much variability in the independent variables is related to the variability in the dependent variable. How much do they move together, either in the same direction or in opposite directions? Okay. All right. So let's load those in. So then I'm going to take this original data set. I'm going to create a smaller version with just the variables I care about. And I'm going to drop the empty ones. Just like we talked about in our previous video, missingness is an issue in regression. We're going to assume missing completely at random. So it's not tied to the values of the variables in any way. And we will drop the missing information rather than put information in, because we don't want to add bias. All right, so let's do that. So do notice that if you're creating this subset, just a heads up here, see these two hard brackets on each end? That's basically saying take these variables inside of this table. And then, of course, we have the last part that is the drop the NA. All right, so then we're going to do test train split. We're going to take those variables. We're going to predict earnings per share. Our test size is 20%. We're doing shuffle equals true, just in case there's an order to this. And the other piece that you don't see is the stratify. The stratify we've used in the other test train splits were because we were doing logistic regression or classification models, where we wanted to make sure that the categories were represented in both the testing and the training data. Here in linear regression, we have lots of different numbers that are in the variable earnings per share, so there's no way to kind of make sure things are in one or the other. Okay. All right, then, like always, call the model, fit the model, and we can then predict with it. So here we call the model, we fit the model. Our focus in these particular videos is on the coefficients, so we can call those. So if we named it LR for linear regression, we could do lr.coeffic with the little underscore there. Will get us the values of the coefficients, and we can do lr.intercept to get that. So with linear regression, our formula is y equals, and then the value of the intercept. So if we were to write this one out, y, which is here is our earnings per share, is equal to 3.98 plus 0.0025 times x1, whatever variable we put first in this formula. And then we have minus 0.001 times x2, whatever we put next, minus 0.016 times x3, what do we got? 1, 2, 3, 4 plus minus 0.0036. Now, how many zeros you have in this coefficient is not really telling you about the statistical significance of it. What it is telling you is that the size of the measurement of that variable is maybe very small. It doesn't change a whole lot. So if the number wavers around between like 1 and 3, then the impact it's going to have, right, may be small. Or if the numbers are really big, then incrementally they're having a little impact. So just because your coefficient has lots of zeros in front of it doesn't mean anything about statistical significance. All right, and then the last variable is x4. X4. Let's try that. Okay, so in this particular case, 1, 2, 3, 4 variables is what we put in: cash ratio, after tax, gross margin, and current ratio. Okay, so we got 4 in there. So there's our formula. And you can't see it because it just all blurs together. So let's try return. Come on. Okay, there we go. So there's our formula. So the question is, what do we do with it? Well, this 3.98 means the average earnings per share is 3.98. And then as we're interpreting this, what we're going to do is take this here, and you can see for the first variable, which is cash ratio, that the earnings per share increase by 0.0025 for 1 unit increase in the cash ratio. And then for the next one, earnings per share decrease by 0.001 for a 1 unit increase in whatever the second one is, after tax return on equity. Earnings per share decreases by 0.01, in this case 0.016. Notice that my numbers are different than the previous run through, and that is because when we do a random test train split, we pull different data to be in the training model, which means it's going to create a slightly different model for that. So that's why each time you run it, when you run it, you're going to get these different coefficients, because we are all randomly sampling from the data set. Okay. 0.0036. Okay, so the last one says that the earnings per share decreased by 0.00036 for a percentage increase, in current ratio. All right, so we can interpret the coefficients and the intercept for our linear regression. But as noted previously, we don't know if they are statistically significant. This is simply describing the sample that we took. And again, if you take a different sample, when you do your test train, you get a different sample, you get different coefficients. So how well does the model fit? Where we can predict, so we, just like we called the model, fit the model, okay, predict with the model, we get X test, okay. We take the testing data and we use it to find our Y, our earnings per share. And then the mean squared error, I'm going to sneeze, comes from, hang on, pause the video. The mean square error comes from taking the Y test, subtracting the Y predicted, okay, and then finding the squared difference of each of those, and then finding the average. So just like we did in our previous videos, when we talked about measurement error, we can find mean square error. It's a built-in function with the sklearn. So we can have it find the mean squared error here. And it, come on, you do it now. So we can see here the mean squared error was 24. For a different sample, it was what, 31. Now, notice we run the R score, the R squared. The R squared here, we could run it on the training data and we can run it on the testing data. So we can do R2 score, and we're going to do it on Y train. Oh, maybe not. Forget that. Never mind. All right. So we have to have a predicted and an actual, and we don't have the predicted from the previous ones. Okay. So we'll run it here on the test and the predicted. Notice that you get this negative number. That is because when it's doing an R squared, it's actually an adjusted R squared. And so when you look at r squared, and r squared, if it is a 1, then all of the variation, and let's say we have two variables, x and y. If you have an r squared equals 1, then all the variation in x explains all the variation in y. They move right together. It's a straight line, okay? Or 45-degree line kind of thing. If you have a r squared that equals 0, then the variability in x doesn't explain the variability in y at all, right? It's just random scatter. There's no relationship here. So when we look at an r squared, we typically have an r squared between 0 and 1. An adjusted r squared says, okay, well, let's also penalize you for having too many variables, because as we add more variables, we should be able to get closer to an r squared of 1, because we can have one variable explain some of the variation in y and have another x explain some more of the variation, and then you could have a model that has 50 variables that explains every little change in your y variable. But that's a lot of variables. You have your degrees of freedom. Remember, they keep ticking down. The more variables you have, the more estimates that are used, and so it is really restrictive. So the adjusted r squared penalizes for having too many variables. Well, notice this r squared is negative because the variables we have don't add anything to the model. And so having more variables that don't add anything to the model give you an even worse r squared, right? So we're penalized for the variables, and the variables don't add anything. So higher r squared, better. We know this one's going to have an issue because, one, all of these variables are highly correlated with each other. And we have this other issue with the data, which is that there's this unknown variable that we haven't included, which is the fact that half the data set, or every 5 data points, is essentially the same company, right? The difference there is time, and we haven't put time or company into the model. So it's not going to fit well because it's the information is about the same company, which would explain why some group of numbers are high and some group of numbers are low. If this is all Apple and this is all Dow Chemical, right? They're going to be different based on that alone. And we've ignored that in this model. So it's not going to fit well, right? All right, so where are we? We can look at the r squared and we can see it's a terrible r squared. Here we could actually plot out the error if you wanted to. So if you want to plot out the error, we're going to take the y-test and we're going to convert it into a format that allows us to calculate the error and plot it. So here you have y-test to numpy, just converts that data that came out, or the to match the formatting we need. We're going to use numpy to do the subtraction. Actual minus predicted. So this is finding the individual errors as opposed to the mean squared error. So this gives us every single error. All right, the average error we're finding here. So the other one was mean squared. It squared the errors and then found the average. This is just the average. Okay, so the average error is 0.16. And whether that number is big or small, of course, depends on what you're trying to predict. We're trying to predict earnings per share, which is a small number to start with, so it makes sense that the error number is small, even if it's a terrible model, because it is proportionate to what how you're measuring. All right, so we can import matplotlib.pyplot as PLT. These other two packages, I put them in here because we can use them later, but really you just need this one here. We'll use this one as we test our assumptions. So that's why it's here. All right, so we're going to plot using plt.plot, plot the error. We'll put dots. We're going to add a horizontal line here. Add 0 because your error should be random scatter around 0. That's what we're looking for. And so we can see the data here. There's some extreme values that we have on both ends. And then we're going to use this residuals to test some of our assumptions. Okay. Now, before we get to testing our assumptions, though, let's just complete the process, which is let's look at the statistical significance of our variables. And to do that, we are going to use that SMF function that we had previous in the other levels. Just going back. So we import our statsmodel.formula.api as SMF. I'm gonna stick that here. Okay, so we need our SMF. We need to put it into a single table, just like we talked about with the logistic regression and the Poisson regression. When we're using SMF, we need it to all be in one table. So we're going to use pandas. We're going to concatenate, and we're going to concatenate so that it's stacking the columns as opposed to adding it as rows below. So that's what this is here. And then we're going to simplify. The thing with this package, this SMF package, is that it's a conversion from an R package. So having columns that have spaces and big long words, it doesn't like. So we're going to simplify this. We're going to take the words earning per share and call it EPS. We're going to take after-tax ROE and just call it ROE. So we're going to just do some renaming here of the columns so that there's just a single word with no spaces. Okay, that's what we're doing here. So we'll do this change, and that gives us this data set here. Names at the top, single word, no spaces. Okay, and then just the variables that we care about, all in one table and not separate like we had with the machine learning method. Then what we're going to do is we're going to take our SMF. We're going to do an ordinary least squares. That's the linear regression approach, OLS, for ordinary least squares. And here we're going to take our earnings per share and we're going to predict it with cash, ROE, gross, and current from the data table we called Reg. Call the model, fit the model, and summarize. Notice the adjusted R squared here is essentially 0. Okay, so then we look at our variables. Are they statistically significant? Well, notice that cash spans 0, ROE spans 0. Those two are not statistically significant. They don't add anything or help us predict earnings per share. We don't include them in the model. We would rerun it without them. This one here, the gross, this one is statistically significant, but barely. The p-value is 0.03. We are looking for less than our alpha of 0.05, so right on that margin there. So we could include this one in here. Notice that current spans 0, has a p-value that's much bigger than 0.05, so it also is not a variable worth including. So if we were to rerun this model, we'd essentially get rid of 3 out of the 4 variables as we explore for a variable that is more statistically significant and helping us predict what is happening. So the only one we have here is this coefficient, this negative 0.016. And so what this tells us then is that as the gross margin increases, the earnings per share decreases. Okay. All right, so we could rerun a model. So this one here, let's add the year. Okay. So if you recall, back in the original data set, we have that period ending. Okay, so we could create one that has, where did it go? It's going to complain because I haven't created it. Let's see. Okay. All right, so we have 4 year. And then we can run this again. So the data set must have one that's called 4 year already. All right, so we're going to do train test split again. We're going to do here 4 year. This one I left the other ones in there, cash ratio, after tax. So you could experiment with them. They're unlikely to add any value, so you could just leave them out. But we could run through this, same as before. We could test train split. You don't have to do the sklearn machine learning. You can go directly to your SMF. Okay, again, if we're doing that, we're going to have to rename the columns to get rid of the multiple words with spaces. So let's create just a very simple model. This very simple model considers year, And notice that this one here has a times in it. In a previous video, we talked about how the benefit of this SMF package is not only could you look at one variable and another variable and how well each one impacts whatever you're trying to predict, but you could also look at the interaction between those two variables. So I think the example I gave was for Poisson, if you were trying to count the number of birds, the type of habitat has an impact on the number of birds. The precipitation might have an impact on the number of birds. They have separate impacts, but perhaps the two combined, the amount of rainfall given the habitat, is what predicts the number of birds. Well, if you were doing this interaction, then you would put this times in this formula here. So notice that when I run this ordinary least squares with the times, it has three variables: return on equity, year, and the combination of the two. So notice in this particular example, all three are statistically significant, both individually and combined, have an impact on earnings per share. So the earnings per share increase with the return on equity, with the year, but when you combine the two and you look at the interaction between, then that reduces the earnings per share. So that is when we look at ROE and year moving in opposite directions, that's going to then reduce it down. So ROE increases, EPS increases. Year increases, EPS increases. But when you start to have the two together, year and ROE moving in opposite directions, then negative impact. Okay, so that's what this model is telling you. You can see it has an adjusted R squared of 0.01, which I think is slightly better than the one we had before. So you can try going through different variables and creating a model that fits better, gives you a better R squared. In the next video, what we'll do is we'll go through the assumptions that are part of linear regression as we analyze them related to this data set, which we know, right? This data set, we're not using it correctly, so it has lots of problems. So let's see if we can flesh that out as we look at the assumptions in the next video.